Okay, time to get started. Let's see. Oh, am I recording correctly? Yeah, it's looking good. Okay, so here we go. Where we were last time, we were talking about spherical coordinates. And remember the definition of spherical coordinates? So you kind of define them, I'm going to say sort of backwards in some sense, right? So we normally think of rho, phi, theta, first, second, third. But you have to talk about what theta is first, so that you can even, have a foot in the door to talk about which direction does theta bend away from the z-axis. You have to know what half plane you're in to know which direction you're going. And then between the two of those, only once those are defined or chosen, I'll say, do you have a direction that then tells you how far rho to go in that direction. Right, so you end up defining them sort of right to left. It's a little bit weird, but anyway. So these are the spherical coordinates, and we did some examples last time. We talked about conversion formulas, and this, sort of geometrically challenging example of visualizing all this stuff in 3 dimensions in 4 different ways. Right, and I think again that's a really good little bit of geometric exercise to kind of get a feel for those spherical coordinates. So I believe I recall I did not write down explicitly what those 4 answers are. I talked through how to think about them and generally how to do them. Right, and I think it'd be a good exercise for you all to finish on your own to think through and write down all of the resulting details. And then, whoever you're studying with, whatever your study group is, compare answers. See if y'all get the same thing. And if you don't get the same answers, now you've got a topic of discussion and an opportunity to get some dialogue going, which I'm a big fan of. Okay. All right. Moving along. So here's a nice, I'll say, application. It's also a way to think about spherical coordinates. There's a close relationship between the spherical angles and longitude and latitude on the surface of the Earth. Now, we set up the Earth in what I'm going to call the usual way, where the prime meridian is like so. It's sort of in the direction of the positive part of the x-axis. North pole at the positive z-axis, south pole on the negative z-axis, center at the origin. What you might expect. And with that settled, notice east longitude is exactly theta. It's saying geometrically it's the same thing. So how convenient is that? Now there's a little bit less happy of an answer when you talk about latitude. Latitude is measured, I'll say north latitude is measured upward from the equator. That's not what phi is. Phi is measured, of course, downward from the z-axis. So they're not the same, but I think you can see that phi and north latitude always add up to 90 degrees, thus giving you this relationship right here. Right, so they're not the same, but they are closely related. And if you know longitude and latitude, then you're a snap away from knowing phi and theta. Right, and of course, if the Earth is set up on our coordinate system as I have it drawn, then the radius of the Earth is rho. And this is assuming that our Earth is a sphere, which of course it's not in a couple of different ways. It's lumpy and bumpy because of mountains and valleys, right? But it's also, I don't know if y'all know this fun fact, because of the rotation of the Earth is a little bit kind of pancaked, right? It's wider at the equator than it is at the poles by something like 20 miles. I've forgotten the exact number, but it's substantial. So anyway, ignoring all of that and treating it as a sphere, easy conversions. So what this does for us is it allows us to answer questions like this. This is a very natural question. But given a couple of locations on the surface of the Earth where you know the longitude and latitude, how would you compute this distance? right? If I wanted to fly in an airplane, shortest possible distance, right? Got to save fuel. I want to be wasting fuel for no particular reason. What is that shortest possible distance? And a lovely answer, and that is to just realize that if you know longitude and latitude of those two locations, well, we have equations just higher up on the page that tell us how to convert that into spherical coordinates. And we have equations on the previous page that tell us how to convert that into rectangular coordinates. And once you've got the rectangular coordinates, then you can say, okay, well, I know the rectangular coordinates of these two vectors. And let's see, by the way, let me clear up the mess. If I know those two vectors, right, I can write down the dot product relationship between them. And of course, computing the dot product is easy because I have the rectangular coordinates. It's just, the usual formula, super easy computation. And the magnitudes of those two vectors are the radius of the Earth, right? So a lot of fairly straightforward and direct calculations allows you to get your hands on that angle alpha. And once you know alpha, you can compute S by, again, a high school geometry formula relating arc length to angle. Okay. So I think it's kind of neat, right? If you don't know spherical coordinates and the conversion formulas, etc., you look at a problem like this, and most people would think of this on the Mercator projection. And by the way, if you're ever, next time you're on an airplane, I always amuse myself by, depending on what airline you're on, right? They have a map showing all of their paths, right? All the routes that they fly. And you notice they always kind of have this kind of curvature to them, and that's because the Mercator projection is all flat projections of a non-flat surface are unavoidably, messed up in some way or another. But that's the Mercator projections problem, is that it makes shortest possible distances look like they're not straight lines. Yes?
How did you know what R1 dot R2 is equal to R squared?
That's a basic fact about dot products, is that when you do a dot product, it's the product of the magnitudes times the cosine of the angle in between. Yeah, that's all that is. Yep. Cool. Okay, neat application. Be a very difficult problem without spherical coordinates and this kind of trickery. Okay. All right, so again, now this is an easy read. If you have a rectangular equation and you want to convert that into a spherical equation, notice it's just a matter of knowing the conversion formulas and plugging in. So, for example, right, we already knew long ago, pages ago, that x is rho sine phi cosine theta. So, boom, you plug that in. No big, right? Sometimes it's convenient to use this one. If you see an opportunity where x squared plus y squared plus z squared is it's part of your equation. Yeah, take advantage of that, right? Don't plug in for x, y, and z specifically if you don't have to. This just saved us a bunch of trig. Right? We would have gotten the same answer if we hadn't noticed, but convenient opportunities. Okay, the rest of the details, make sure to read. Okay, I have some bad news. Not all conventions for polar coordinates, spherical coordinates, etc., are the same. There are different conventions that get used in different contexts, and I'm sorry. It's not my fault. This has been around for a very long time. There are actually pretty good reasons for this, and it's a long and intricate discussion of exactly why, and part of the problem. So, for example, where's my pen died. Let me plug this in. Pull out my spare. Here we go. So, part of the problem is that, for example, the letter rho that we use for kind of the, if you will, the radial distance coordinate. And spherical. Well, that is also used for charge density. when you're doing electricity and magnetism. It's very standard. So, well, that's super confusing, especially because when you're doing electricity and magnetism, spherical coordinates is often a powerful tool that you do not want to have to live without, right? So if you're using spherical coordinates along with charge, you can see using rho for two different things in the same context would be a nightmare of confusion. So anyway, heads up about this. There are different conventions. Here's the what I think would be called the standard physics convention, and that is to use r, not rho, to represent that radial distance. I mean, we use the r vector to indicate that position vector. Pretty reasonable choice, isn't it? Right? Okay. And then here's the one that's super frustrating for me, and that is what our book uses phi to represent. The standard physics convention is to call that theta. And what our book calls theta, the standard physics convention, is to call that phi. And it's frustrating, right? So the only solution that I am aware of to this is heads up, right? So don't just go all in on one coordinate notation choice, because you can't, because you're going to be taking classes where they will use the other convention. That's going to happen, right? So you have to be ready for that. Now, that said, our textbook does seem to use the convention that I showed you, right, pretty consistently. So there's that. All right, and that's nice. Certainly, if you're doing any book exercises, follow Colley's convention, namely the rho phi theta that we've been using. But for example, if you're taking an exam, hypothetically, right, in this class, and if the exam establishes a convention, you have to stick with that convention, right? You can't say, well, I like to do it the other way. You can't do that, right? They would create massive confusion, and it's just not a good precedent, right? You have to be able to be proficient working with both of the conventions. So stay with whatever convention has been established, and likewise, if there is no established convention given, and you're the one that came up with the idea of using spherical coordinates, right? You can choose any convention, so your choice of convention, just make sure it's clear and stick with it. You can't switch conventions halfway through your solution, right? And you can't just kind of never getting around to saying which one you meant was what, with the expectation that we'll, assume you were doing it the right way. Because, again, you have to demonstrate what you're doing. You have to be unambiguous about what you're doing. Okay. All right. So, by the way, here's how to make it unambiguously clear. Excuse me. Let's see, cleared up a mess. For example, you could say r theta phi, right? And the understanding is always that whatever you list first is the name you're giving to the distance coordinate. Whatever you list second is what you're assigning to the vertical coordinate. Right, and what you're listing third is what you're using for the horizontal coordinate. So that ordering of distance, then vertical, then horizontal, that's non-negotiable. That's always got to be like that. But so anyway, with that established, if you just write down r theta phi like this, that's understood. That means that you're doing this, and go about your solution. Right? Alternatively, of course, you may also indicate rho phi theta. Right? This, again, unambiguously clear. Distance coordinate, vertical angle, horizontal angle. Right? And that's the book's convention. This is also pretty common. Okay, so heads up about that. Now, just to put your minds at ease a little bit, how is this actually, in fact, kind of okay and not as bad as it seems? I'll point out that there are lots of situations where this happens, right? Now, y'all are probably accustomed in a lot of math classes that that's X and that's Y, right? Take an econ class. There'll be P and Q. Right, so they use different conventions appropriate to the circumstance, and it's not that big a deal, and it's something you just deal with in the context. Right? So this is really kind of the same thing, just it's a little bit weirder because it's a little bit newer to us. Right? But ultimately, it's just kind of a matter of getting used to being able to think independent of the angles that are being described. Yeah, I hope that's working. Okay, all right, moving along. So standard basis vectors, y'all remember standard basis vectors. I like to use this notation most of the time. There's a few exceptions, but it's very convenient to have the flexibility to talk in whatever dimension you want, right? If I'm using E1, E2, E3, I can do that in R17 if I might need to for whatever circumstance. Okay, also commonly known as IJK. Also, commonly, sometimes, with a little hat, little triangular hat instead of the vector symbol. And that hat is an indication, kind of a reminder that, hey, by the way, just to be clear, these are unit vectors. That's all the hat means. And this is what they are, and they're super useful for a lot of things. And I know y'all have seen those things. We talked about some at the start of class, how they behave very nicely with respect to linear combinations, total ways. Okay. All right. So there's a different way you can think of them. These are the unit vectors that point in the direction where you're increasing a single coordinate. And the other two coordinates are, at least at that moment, not changing. Right? So just think about it, with a 0, 1, 0 points in the direction where y is changing, x and z are constant. Okay. So this is something we can generalize, and it's a nice little collection of geometric exercises. Now, you don't have to do the actual evaluating of these vectors suit yourself. I think they're nice little geometric exercises, and if you're in the market for make sure that you're good with the details of what's going on here, give them a try. Right, here's what the answers are. But notice these formulas do what we claim. For example, if I'm at this point, notice that what I'm calling ER, that vector, points in the direction where r is changing and theta is not. Right? It's a unit vector pointing in the direction where only that one coordinate is changing. And likewise for the others. Again, a good little exercise. These are pictures of what all of these standard basis vectors look like. I'll point out real quick that notice the E phi vector. Right? That's imagining that you have a position vector like this. Phi, of course, is this angle. Right? And so what direction do you go when phi increases? Well, you would be going that way. Right? As phi increases, you'd be going kind of downward. And at least at that point that I have gone there. How are we doing? All right, so these vectors are useful in various circumstances. We'll use them a little bit in this class, not tremendously, but a little bit. And you will also see them outside of this class in other contexts. Okay, a couple of things to keep in mind. Again, rectangular coordinates are peculiar. In rectangular coordinates, the standard basis vectors are always the same. No matter what point you're at, the standard basis vectors are always the same. Not so in the other coordinate systems. You'll notice that as the point moves, those standard basis vectors change. So that's weird. They also don't behave nice with respect to linear combinations, right? So this right here is this awesome relationship where if you know the coordinates of a vector, that tells you the coefficients in a linear combination. In fact, y'all may recall from your linear algebra class you took recently, that's kind of the definition of coordinates, right? So anyway, super handy, depending on how you want to look at it, either handy or fundamental. Nothing of the sort is true in spherical coordinates, for example. It's just not true. Just doesn't work. Doesn't make any sense. Okay. All right. So again, though, they do have some uses. And by the way, neat observation. They're orthogonal in all of our new coordinate systems. And that's kind of a coincidence. Arguably, one of the things that makes us like this coordinate system, these coordinate systems, is that the standard basis vectors happen to be orthogonal. Anyway. Okay, so moving along. A bunch of stuff to read here. Again, you know, tough choices. We have the looming specter of chapter 6 and 7. Very challenging, lot to discuss, lots of pictures that need to be drawn, a lot of ideas that need to be sort of soaked in, and so readable stuff that you can do on your own is, the more of this that we leave to y'all now, then the more time we'll have to spend time in class dwelling on the much more challenging ideas of chapter 6 and 7. So a lot to read here. I do want to say a couple of words about some of this. A lot of people misunderstand what a function is. A lot of people think a function is, like some formula that you write down, and that's part of the story. But a function is a trio. It's a domain along with a target. Some people say codomain. Target, to me, is more visually satisfying. And what we call a rule of assignment, otherwise known as a formula, right? That's the more familiar part of a function. But very importantly, the word function refers to the trio. So for example, let's talk about what I like to call the student ID function. For any student, there is a corresponding student ID number, right? Like 7-digit number or something. Okay, so with that understood, let's think about these two functions. These two functions. Right, these two functions, f and g, they're both defined for all students. In both cases, student ID is going to be the rule of assignment. That's how we're going to compute the output value for any given input student. Seem like the same function so far, right? For every student, you give me the student ID. Aren't we done here? Sadly, no. These two functions have different targets. In the top function, we view the output value of the function as being necessarily an integer, which of course it is, right? Nobody has a fractional student ID. That'd be weird. But in the bottom function, I'm just simply requiring that the student ID be a real number. Those are different sets. These two functions have different targets. These are different functions as a result. And I know that seems extremely fussy, right? I mean, what's the big deal? I mean, we know these outputs are all integers. Who cares if I allow the flexibility in the second one that they might be real numbers, and why are we upset about all of this? Seemingly pointless fussiness. So let me show you an example of why we care about this kind of thing. This is just one example, by the way. And by the way, again, make sure to read. There's some language set up here, some definitions. Make sure to read all that. It's kind of in this context building up to this idea of invertibility. So I've got some sort of figurative pictures drawn here of hypothetical functions. In each one of these four instances, we have kind of the set on the left, the set on the right. That's the domain and the target, respectively. And for example, this function on the far right here, for every point in the domain on the left. There is a corresponding point in the target on the right. And this is what I will call an invertible function, because I can turn those arrows around backwards and I get a different function. That's all we mean by invertibility. I can say, how about this? And now my domain of this new function, I'm writing down, my domain is this set on the right. And for every point in this set on the right, I can follow the green arrows, and there is a corresponding, perfectly well-defined point on the left. Okay. So now y'all are familiar with the idea of an inverse function. This isn't new to y'all. There's a little bit of abstract take on it, but this is the idea of an inverse function. And the thing is, if you're going to describe this as a function, it's kind of a big deal, right? We want to be able to do calculus with it. Calculus applies strictly and only to functions, right? I need for this to actually be a function. And look what goes wrong if your function isn't invertible. If your function doesn't look like this specifically, right? Then you have problems like, like you look at this. Let's look at this function right here. I can turn these arrows around the other way, but I've got a problem with that point. If I claim that I have an inverse function here, I can't even tell you how that would be defined at this point in what needs to be the domain of this alleged inverse function. So I can't describe this as being an invertible function because the inverse as a function doesn't exist. There is no way to make sense out of that. And there's an analogous problem that happens in a case like this. Let's think about this point. I mean, does it go there or there? Remember, when you define a function, the rule of assignment has to unambiguously give you a well-defined output. That single output can be various, whatever. It could be whatever element of whatever set your target happens to be. But it does have to be unambiguous. And here I have an ambiguity. I don't know where that purple point's going to go. I've got a couple of different options, and it just doesn't work. Right? So you can't make sense out of invertibility unless you're particular about what the domain is and what the target is, so that you can check this requirement as we're discussing here. Okay, now this is glossed over in most single variable calculus classes, but here's a couple of examples, and again, mostly for y'all to read, but I think these are pretty persuasive examples of, look, you really have to make sense out of what is this inverse function you're talking about, and you can't do that until you decide certain choices. So, for example, this function here, it's not invertible. It's like straight up not invertible. If I look in its target, if I look at the point 25, what would be f inverse of 25 here? Is it 5? Is it negative 5? I've got too many choices. Right? Problem. Likewise, what's f inverse of minus 4? I got nothing. There is no real number whose square is minus 4. Right? So dead in the water. But if I do this, if I restrict my domain, just the non-negative reals for the domain, just the non-negative reals for the target, everything works just fine. The squaring function from non-negatives to non-negatives has this feature that for every point in the for every output there's exactly one corresponding input, and therefore I can talk about the inverse function, and therefore I can do calculus with the inverse function. And we've discussed this previously, but this inverse is what we call the square root, and remember that symbol right there means the positive, non-negative anyway. square root. Okay. All right. I'm going to let y'all read this next example about trig. It is something that is glossed over in most high school trig classes, in my experience. A lot of people mistakenly think that arcsine is just, it just undoes the sine function. Well, that's ambiguous, right? Again, you have to restrict the domain. Bad color choice. You have to restrict the domain to just these input values and restrict the target to just these output values. And now, sure, for every blue output, there is exactly one corresponding green input. That's invertible, but only because you restrict the domain and target. So, likewise for the other 5 standard trig functions. And so, by the way, it's a good idea to make sure that you're clear on what all those conventions are for what are the allowable angles and stuff like that. So again, make sure to read all this and then think about the analogous arguments for the other functions. Okay, terminology. Make sure to read. Again, important, but not really worthy of class time. It's just language. Just make sure to read that and retain. And I like this example of a vector-valued multivariable function because it sounds like such a complicated thing, and in fact, all we're talking about is the weather. Right? It's a neat observation, but you can't talk about the weather without telling me where you are, longitude and latitude, how high above the ground are you. Makes a big difference. Right? It's a lot colder if you go 35,000 feet up. And when? Are you talking about the weather now, or are you talking about the weather last week? Right? They're totally different. So those are inputs, and then with those inputs, we can talk about, as output values, we can talk about, the temperature and the barometric pressure and the wind speed and the humidity, and you could probably a bunch of other stuff that you could include if you like. But notice there are several inputs, thus making this a multivariable function, and there are several outputs. Said differently, the outputs collect together to form a vector. And so vector valued, because the output values of this function are vectors. So, very, very, very useful to understand these kinds of functions. Okay, moving along. How to draw pictures of functions. I like to spend a lot more time on this than the book does. The book, I think, undersells this. My experience in teaching multivariable calculus for a long time now is that this is one of the big examples of students being a little too quick and dirty, a little too fast and loose, a little too careless, a little too sloppy about the relationship between pictures they're looking at and algebra that they write down to describe said pictures. Or vice versa, algebra that they're looking at for whatever reason, and then the pictures that they draw to help them understand that algebra. Right? So we need to be careful about this because there are several different ways to do this. There are several different ways to make pictures that represent functions. When you do calculus on the function and you've got a bunch of different pictures to look at, well, how do you interpret that calculus? Well, it depends on which kind of a picture you're looking at. If you generate a totally different picture by a totally different process, calculus will look totally different. Right? It's an important distinction. And so if you're going to interpret calculus appropriately, you can't be unclear as to exactly what kind of a picture are you looking at and therefore what sort of interpretations you should make. So there's a lot of details about the specifics of how do you interpret multivariable calculus geometrically, and we'll be doing that as we go through the next several chapters of the book. But this is sort of underneath it all. You've got to know what kind of constructions you're looking at. So we're going to start talking about the graph of a function. I know y'all have done graphs before. You might not have used that word, or you might have used other words in sort of instead. But if you have a graph of a single variable function, it looks like this. Y'all have seen that a million times. Okay, what exactly is the process that makes this picture? And there's a couple different ways to think about it. As I have it drawn in the optional, by the way, I made this definition optional just because there's a lot of notation, and I don't want you all to get distracted by notation. Right? But the big idea is that a point on the graph has coordinates, the first of which are whatever the input to the function is. Right? And the second of which, or the next of which, I guess I should say, are whatever the output is, or whatever the outputs are, however many of those there may happen to be. Right? So you take the inputs into the function, the outputs out of the function, you smash them together like so. Those become points. And when you do this same thing for all possible values of x, then that produces what we call the graph. In this case, curve. Okay, so I hope that looks familiar. Maybe it's a different take on it than you've seen before, but that's one take. Now here's a different take. I like to point out that when you write down a function, typically like a single variable function, typically you write down something like this, and again, you establish as part of that function, keep in mind a function's a trio, there's a domain, there's a target, and then you've got to be explicit about what is your, loosely speaking, formula, right? Your rule of assignment. Given an input, how do I know what the output is? You've got to be explicit about that. So there's your trio, there's a function, and notice what I have highlighted in purple there. No y anywhere in what's set up in purple. So I just want to emphasize we are choosing to write y equals, to take these output values and give them a name, call them y, and then to write down this equation, to write down y equals f of x. Right? That is a non-required choice that takes a function and produces an equation of which I can draw the set of solutions, and that too gives me the graph. So you can think about a graph either way. You can think about it as a bunch of points where you put the inputs and the outputs kind of together and put all those points on the page, or you can think about it as a graph is what you get. Let me streamline a little bit. A graph of a function, given a function, the graph is what you get when you set those output values equal to y. Or some other, depending on what your input variable is, some other variable, in this case y. Okay, so with that in mind, let's think about a multivariable function, right? Let's think about what if I have two input variables. Right, so here I've got two inputs, x and y. We put those first. I have one output. You can see we're choosing to call that z, arbitrary. You put that next, and again, that gives you a bunch of points. Notice that for every x and y, there is a corresponding z, and that produces a point. And again, if you do this for all the inputs, then you get, in this case, a surface. Right, so it's not a curve in the plane. Here, with two inputs and one output, the graph is a surface in space. How are we doing? Does that make sense? Everybody see how this is kind of a rip-off of what we did in the single variable case? Same idea, just extra input variable. Geometrically pretty different. All right. We will talk later about how to do calculus for a function like this. There's some big questions there. What does that even mean to do calculus on a function where there's multiple input variables. A lot of ugly questions there. And we'll deal with it. And then the natural next question is, geometrically, what does that calculus look like? If I am able to successfully write down some calculus algebraically for these kinds of functions on the graph context, what does it look like? Does it have something to do with slopes? Maybe. I don't know. We haven't defined the calculus yet, so who knows what we'll come up with, right? But there will be the question of what geometrically it looks like. And when we get to that, when we get to this process of trying to understand calculus and what it looks like on the graph, I'm going to call that the calculus of graphs. And there's a fair amount to say about the calculus of graphs. Calculus of graphs is a very useful part of this course. And it is not the only useful kind of calculus that we're going to talk about in this course. So keep that in mind. Okay. All right. Now, let me try to break you of a possible dependence crutch, using graphs a little too needfully. And so let's think about this function right here. Right now, 3 inputs, 1 output. Let's take stock here for a moment. This is the second simplest multivariable function that we can write down. Right? The simplest is 2 to 1. 2 to 1. That's the smallest number of variables that are multiple, right? So 3 to 1 is the second simplest. It's about the simplest that you can ask for. And yet, if you think about it, when you form the graph, whichever way you think about it, notice you're talking about 4 variables. That means that this would, if I were to try to draw the graph, it would live inside of a 4-dimensional space, and I can't visualize in 4-dimensional space very well, which I say as a joke. I can't visualize in 4-dimensional space at all, right? I can fake it, right? But I can't actually geometrically visualize that, and neither can you. So this graph construction that was so useful in Calc 1 that it's the only picture they even tell you is useless in this not very advanced looking example. Right? So the graphs are nice. They have their purpose. They're particularly nice in single variable calculus. They are absolutely not good enough in a multivariable context. Everybody see my reasoning there? Everybody buy it? So again, get used to the idea that you're going to have to figure out how to deal with different kinds of pictures. Oh, my pen's working again. Good. Okay, let me put my spare back in here. Okay. All right. Okay, here's a different one. That's what I like to call the literal picture. By the way, I'm not sure if there is a formal name for this kind of a picture. This kind of a picture gets drawn in many, many circumstances. This is not something that, this is an extremely routine picture to draw. But the name I've never actually seen written down, so I'm just calling it the literal picture, and that's what we'll go with here. So it's the reason I call it the literal picture is because you are literally going to take the domain and we're going to draw it. There's my drawing of the domain, R3. That's how I draw 3-dimensional space, right? And then I'm going to take the target, R1, and I'm going to literally draw a picture of R1, the real number line, right? That's how we draw that. And then what the rule of assignment is, this process of taking points out of the green space and plopping images down into the blue space, I'm just going to represent like so. So for example, this point that I have labeled as A, right? Its output maybe is that point F of A. So there is a kind of a picture. And I think that's at a first glance, pretty disappointing, right? It's a letdown. Where's the picture? How do curves and surfaces, I can kind of, the shape of the graph tells me stuff about the calculus. I feel like I've got, I've got my hands on it somehow. I've got a foot in the door to using geometric intuition to help me understand the function. Where's the picture here? And there isn't one. Not much anyway. Right? So a lot of people make the huge mistake of thinking, oh, well, then this is useless. And I can't imagine why anyone would want to use this construction, and that's a terrible, terrible mistake. Let me try to persuade you why. The case that I just made against this kind of a picture was deliberately unfair, because I was comparing what the graph construction does to 1 and 2 variable functions with what the literal picture does to a 3 variable function. Now let's play fair. Let's compare this 3 variable picture, the literal picture, against what the graph does in a 3 variable case. And remember, that's this that we talked about right here. So which is the better picture? A disappointing picture or nothing? That's your choice. You have a choice between nothing or disappointment. And I suggest that you take disappointment. Does that make sense? This is a beggars and choosers situation. Right? It's like, well, it's better than nothing. By the way, here's an example of how this can be pretty useful. And I think this is really very useful. If this is my scenario, I could reasonably ask the question of, well, if I'm at that point A, what happens if I start moving? Now, reasonable appeal. If you start changing the inputs to the function, well, the output value is going to change. And so there will be some relationship between the velocity vector of my movement in the domain and the velocity vector in the target. Now, how do we do that? Yeah, that's a question. Sure, we'll get to that. No worries. But one thing you got to give me, that picture kind of describes the question that we just posed. I can see the movement in the domain. I can see the resulting movement in the target. I've got a useful picture of the relationship that I'm looking for. Much better than nothing. Okay. All righty. Okay, let's talk about level sets. By the way, how am I doing on time here? Let me find the... Hang on a second. Oh, yeah, okay. We got a lot of time. That's great. Okay. So let's talk about level sets. Again, there's a bunch of... Don't get distracted by the notation and such in the definition there. The big idea of a level set is that you establish... You establish some point in the target, and then you ask, what are the corresponding inputs? You see there, x, that what I'm calling x vector is an input. What are those corresponding input values in the domain? It's kind of sort of like turning a function around backwards. If you just want to play with a function, you say, hey, here's an input, what's the corresponding output? We're just turning that around backwards and saying, hey, for a given output, what are the possibly multiple, sure, I'm not saying there's an inverse function, but what are the possibly multiple inputs that produce that output? So, for example, let's just get into some explicit algebra. Here is a multivariable function. Right, domain R2, target R1. There's the formula. There's our trio. And I can start asking questions like, okay, well, for, let's see here, okay, let's do it like this. For this output value 1, what are the corresponding inputs? What are the points in the xy plane that when I plug into that function, spit out the value 1. Right? So what points can I put in that'll make the output equal to 1? And I think you can persuade yourself that what I would need is I would need x and y to be points where x squared plus y squared is 1. In other words, I need points on that circle. So this is a first example of a level set. Given the output value 1, the corresponding level set, pre-image we call it, is that circle. And by the way, notice the terminology, the notation that we use. F inverse, sort of recognizing that we're sort of going backwards, and the output value that you selected is in parentheses next to it. And you can do this for other points as well. You could ask, okay, what about for 2? Right? What's F inverse of 2? Well, I would need 4x squared plus y squared to equal to 2. That's this circle, which we denote like that. That's F inverse of 2. Everybody on board? Okay. All right. Here's a lovely example. This is, I find, very intuitively satisfying. I'm going to talk about the altitude function. The altitude function I'm going to define very simply. If you give me a point on the map, longitude and latitude, the altitude function says, okay, literally what is the altitude of the surface of the Earth at that map coordinate point on the surface of the Earth. So you give me longitude and latitude, 2 inputs in, 1 output out. Now, I could talk about the graph of this function, and I could draw that graph, and then if you think about it, the surface of the Earth, right, the topography, the mountains and valleys, etc., all of that kind of is the graph, because longitude and latitude really are the kind of the horizontal, the sort of the x and y, if you will, and then the altitude really literally is the z. So, the construction of the graph actually literally reproduces the mountain. And that's all well and good, except for the fact that I need something that I can fold up and put in my pocket because I'm going on a hike, and I don't want to have to carry around a plaster model of the mountain as I hike, a hard hike. Does that make sense? Okay. The three-dimensional picture is not that helpful. But level sets work great. So I can talk about, for example, maybe let's say 100 feet altitude, and maybe that is the collection of points where altitude is 100. Some sort of curve like that, right? And then I can talk about, okay, well, what about 200? So that's the set of points where the altitude is 200. And then we can do 300. Where is the altitude 300? Et cetera, et cetera. And so for each of these possible altitudes, you draw these corresponding curves. By the way, these are called contour lines in practice. Like if you look at an actual topographical map, if you actually are going hiking, people don't say level sets, right? But they're called contour lines. And this is actually really, really helpful. So I think you can see a lot of useful information just by looking at the contour lines. So for example, and I'm going to zoom in so I can see a little better. If I were planning a hike, and if I were going to be starting here, and I want to get to there. Now, when I was a kid, I'd be like, okay, straight line. I'll just climb right up that mountain. What is that? 400 feet of elevation over a very short horizontal distance. That'd be super steep, and that'd be a lot of fun when I was at y'all's age. Right? But nowadays, Nowadays, I'm like, okay, let me kind of hug this contour line for a while. That's nice and level. Now this is slightly uphill. And notice I've worked my way over to where it's not that steep, and I can get where I need to go, and I didn't have to go over it. I didn't have to do any super steep hiking. That was a nice, gentle, pleasant hike. Everybody see what I mean? And again, you can see that just by looking at the contour lines. So level set, this is an example of level sets, and it's very, very useful. By the way, I do have, just for your possible entertainment, this is an actual contour map of a region that I did a little hiking in when I was y'all's age. Some interesting things that you'll notice about it. You'll notice that along in here, it looks super steep, right? And you can even kind of visualize how steep it is because you look at the elevation there, and then you look at the elevation like there, and over this very short horizontal distance, you drop like, I've already forgotten, and it's hard to count those little lines, but it's like 800 feet over not very far horizontally. It's bonkers steep. It's like when you're up there, you will swear it's straight down. Right? It's extremely intimidating. And you can see that again on a flat two-dimensional map because of understanding contour lines, aka level sets. Let's see here on the hike up, you'll notice the trail does these what are called switchbacks. Right, that little zigzaggy pattern there. If I can get this to zoom in. Come on, there we go. So why do we do that zigzaggy pattern? Well, it's kind of the same reason as what I was talking about before. If I wanted to get from here to here, I could do all of that altitude gain over a short horizontal distance. That's going to be pretty steep. Or I could accomplish the exact same amount of altitude gain over a much longer horizontal distance. That's going to be less steep, right? And depending on how steep it is and how out of shape you are, that can be very much appreciated. And along in there, by the way, it's no joke. It's pretty steep. I don't know. It's about like that or something. You get tired fast. The fact that you're at 12,000 feet doesn't help either. Okay, all right. So thus the idea of switchbacks. Okay, I thought that was just a fun little sort of real-world scenario. Okay, back to the notes here. Here's a neat fact. Hang on. I wanted to get back into the. Here we go. Level curves are horizontal cross sections of graphs. It's nice and pithy. There's quite a bit going on in that sentence, so let's think about it. What are we looking at there? Well, if I take a graph, that's what a graph is. A horizontal cross section of that graph would be the act of saying, well, horizontal cross sections like this. I want to look at points at a particular value of z. In other words, I want to set z equal to a constant. And notice that the result of that horizontal cross section, if you put it together, let's see here, put it together, you're just saying that f is equal to c, and that's what a level set is. So literally horizontal cross sections of graphs. So a geometric example. So let's just straight up do one. We've already studied this function, and we've already talked about its level curves. Its level curves are circles, kind of concentric circles, centered at the origin. We talked about that a page back or two. And then let's see here. What about the graph? Now, I'm going to justify the following later. But if you take the graph of this function, and keep in mind this is one of our points of view on graphs. The graph is what you get when you set the outputs equal to a new variable. X and Y here are both inputs, so I'm going to set f equal to z. Right, that gives me my graph. I'm going to claim here and demonstrate later that makes a bowl like this. And you can, to some degree, you can maybe kind of persuade yourself of this a little bit, kind of notice if y is a constant, then you clearly have a parabola. You can kind of see parabolas in the x direction kind of in that picture. And if x is a constant, then you have z equals y squared plus a constant. You have a kind of a parabolas in the other direction. I hope that's not an implausible picture. But again, I'll make a more careful argument about why that is the right picture later. But that said, let's think now about what happens when you take the horizontal cross sections. Horizontal cross sections like so. Right? Depending on which horizontal cross section, I'd have different values of c. Well, if you take z equals c and plug that into there, then altogether, you get concentric circles, aka the level sets. Is that cool? Everybody's happy? There is something a little bit annoying about this fussy little point. A perfectly reasonable gripe would be to say, hey, those aren't the same. Look, these circles here are suspended up in three-dimensional space. Those circles are all in a two-dimensional world, just the XY plane. There is no notion of altitude. So are they really the same? And fair gripe. They are not technically quite the same. When I say they're the same, what I mean is they have the same equations involving x and y. And yeah, sure, with one of them there's a third coordinate, the other one there isn't. But as far as x and y are concerned, they're the same. Okay. All right. Okay. So let's see here. I want to do a quick time check here. Bear with me a moment. Yeah, we're good. Okay, so because we have until 11:20, is that right? Okay. Okay, so I already said some about this, that we are going to have to deal with different ways of understanding functions. Graphs are fabulous in single variable calculus. They're useful in multivariable calculus, but they are not the end-all be-all, and they are not the only tool. We cannot get by with just graphs. We've already seen now we have these things called level sets. Right? Oh, hey, side note. We've already seen these things called parameterizations. If you think about it, a parameterization is a function that relates to a curve. Right? So it's another sort of example of where there's a function and there's a corresponding picture. So we have now 3 different tools to, depending on how you want to say it, relationships between functions and pictures. And they're all different. Right? The graph of a function is not the same as level sets of the function, which is not the same as what you're parameterizing by the function. They're all different pictures. Okay. So now again, I've already made the following observation. It's important that we understand that they're different pictures because we're going to make different interpretations of the calculus appropriate to those different pictures. And if you take an idea from the calculus of level sets, whatever that is, right? We'll get to that soon. If you take an idea from the calculus of level sets and apply it to a graph, that's nonsense. You're going to get garbage answers. Right? So we got to be really careful about this. I think a nice way to see this is to kind of turn it around, and instead of saying, hey, here's a function, let's think about all the pictures we can produce. Let's say, hey, give me a picture, and let's think about all the different functions that we can relate it to. Right? So as you'll see here, I'm talking about a line that has this equation, and that's an easy picture to draw, right? High school algebra, make sure you can do that, of course. What function describes this curve? Now, this is where a lot of students, especially, in high school context, would just kind of, write down something that seems reasonable or whatever, right? But we're going to be very, very careful about this. We have to be very, very careful. There are actually 3, and that's just using the tools we have so far, 3 different functions that relate to that one curve by way of these different constructions. And I think this is pretty believable that if I look at this first function called f, if I take the graph of f, which of course I do by setting that equal to a new variable, let's say y, there's our graph of f. Right, well, it's not hard to persuade yourself that that is algebraically equivalent to the equation in question, namely the line L. By way of the graph construction, right, the line L is the graph of that function f. Okay, right, true, but what about this? Notice that if I want to talk about level sets, right, level set is what you get when you set your function equal to some designated output value, namely you set it equal to a constant. And notice that too. If I choose the appropriate constant, 6 gives me that same line. So this line, it relates to that function f, but it also, in a very natural and important way, relates to this function g. Okay, so now here's a rhetorical question. Looking at this situation, if I want to understand the geometry of that line, which one of these functions should I do calculus on to understand that line? I got 2 different choices. How do I choose? Which one's the right one? Does everybody see the problem? Okay. So the answer is it depends on what you want to know about the line. The calculus of graphs applied to f will tell us some information geometrically about L. The calculus of level sets that we will talk about over the next, couple weeks here and there will tell us different, also very useful geometric information about the exact same line L. And so it's, yes, you have to know the calculus of graphs, yes, you have to know the calculus of level sets, but you've got to keep them distinct in your mind so you apply the right kind of calculus to the correct function. And again, if you get them mixed up by being sloppy, you're going to get dramatically wrong answers. How are we doing? Is everybody with me? All right, this is one of my soapbox topics, so I may be dwelling on this too much. Oh, here's a nice exercise. You can totally do this yourself, but this function here parameterizes the line. Make sure you can see where that function comes from. Reminder, we did talk about how to parameterize lines back in early chapter 1, right? And so that is yet a third function. And by the way, there is a calculus of parameterizations, calculus of parametric curves, and that will tell us yet different geometric information about the line. Okay. All righty. Okay, moving along. I've already kind of effectively talked through all of this. Okay, well, let's see here. Sometimes it's nice to be able to kind of switch between these 2 different constructions. And it turns out that this trivial little bit of algebra right here is super valuable little bit of trivial algebra in this situation. So notice, by the way, let's take a quick moment to notice how trivial that algebra is. All I did is I took the right-hand side and I subtracted it over to the left-hand side, right? Nothing happened there. That's the easiest of algebra 1, right? Okay, well, what I had started with, you'll notice, is a graph, right? You can see I've solved for one of the variables in terms of the others. I made that a little too... There we go. So this is a graph, and it's a graph specifically of that function there that I'm calling f. You'll notice that there are n input values. There's one output value. So that first equation there is literally a graph. If I want to understand whatever surface this describes, whatever kind of geometric critter that is, right? If I want to understand it with the calculus of graphs, f is the function to which I apply the calculus of graphs. Cool. Okay, but notice the same equation, morally, is also a level set. Right? This bottom form of the equation. Stuff equals constant. That's how we form level sets. It's a level set of not f. It's a level set of this function g, which you will notice has n plus 1 variables. Right? All of the x1 through xn, yeah, sure, that goes into the formula for g. Right, but I also need to know what y is if I want to compute that left-hand side, namely if I want to compute that new function g. Y is now an input variable. So if I want to, for whatever reason, now same surface, that same, what I have described in purple there, morally just one equation. If I want to understand that with the calculus of level sets, don't use f, but use g. So, right, okay, fine. So, but who cares? What's the point to this? And the point is that sometimes, and this happens surprisingly often, sometimes you have a graph, but you want to use the calculus of level sets. Calculus of level sets is really cool. There's some neat tricks. There's some fabulous little geometric, results that I can get if you use the calculus of level sets. So if something comes to you as a graph, you don't have the right function. You have the function whose graph is your object. You need to figure out how to view it as being a level set of something so you can use the calculus of level sets. And that trick up there is exactly how you do it. And again, super easy algebra. Right? Doing this is super easy, but it does have to be done just so. Right? And you can't be sloppy about this kind of thing. Okay, so let's see an actual hands-on example. So here we go. Suppose I am asked, for whatever reason, I am interested in the graph of that function f. That's some surface. And I claim it's kind of a bowl shape. Again, we'll talk about that later on. Pretty soon, actually, probably. Not today. But if I want to understand that bowl, calculus of graphs by applied to that function will tell me some of the aspects, geometric aspects of that surface. But what if I want to use the calculus level sets? Calculus of level sets will tell me different geometric information. I can't apply the calculus of level sets to that function because it's not a level set of that function. So all I have to do is just make sure to be explicit in noting that my surface, in being the graph of that function f, that is equivalent to a level set of this function. And so what I will do when I want to use the calculus of level sets to understand this thing whose graph I was given, I would apply the calculus of level sets to that function, not f. If you apply the calculus of level sets to f, you get nonsensical garbage. Everybody see what happened there? Okay, so the thing about this is it is actually trivial algebra, so it's really easy to get it right. But it is also extremely rigid. It's fussy. Close is not close enough. You got to get it exactly right. And the sloppiness that most high schools allow in situations like this is not okay. So despite, of course I make a big deal out of this, right? I've been harping on this for half an hour now. That little bit of fussiness is what goes wrong for tremendous numbers of students. And the bigger deal I make out of this, the less students step on this landmine and mess it up. Real quick final example, just notice it only goes the one way. If you have a level set, it's not necessarily a graph, right? So for example, here I have very conveniently that this is a level set of that function. Right, so this equation is this circle. That's definitely a level set. It's a level set of G. It's not a graph of anything because you can't solve uniquely for X or Y. It's not a graph. You can't use the calculus of graphs here. Y'all have a good rest of your Tuesday. See you later. Have a good one.